Hello, Chem 1A. This is Chapter 7, Lecture Video 4, and we're going to be discussing the ideal gas law and density of gases in this lecture video. So let's talk about the ideal gas law. This is one of the last laws that we learn about, and by far probably the most useful one in this chapter. It is PV is equal to nRT. Now, these are very familiar unit variables, as P means pressure, V means volume, N means moles of specifically has to be gas that we're using in the ideal gas law, and R is the ideal gas constant, which is a given value that I'll always provide, is 0.08206 atmospheres times liters over moles times Kelvin. Now, because of the units in this constant, all of our variables here have to be in specific units. Pressure has to be in atmospheres. Volume has to be in liters. Gas, N, has to be in moles. And finally, T has to be temperature, specifically in Kelvin. Again, we're in Kelvin here. Now, using this equation is slightly different than the previous ones we've talked about because it's not a two-point equation. There's no initial condition, final condition. This allows us to calculate the pressure in a container if we know the volume, moles, and temperature. Or if we know pressure, volume, and temperature, we can calculate how many moles of gas are present. It actually adds another way to get to moles so that we can do stoichiometry if we're dealing with gases. And we'll get to that in a later lecture video. So what is an ideal gas? Why is it called the ideal gas law? Well, when we assume behavior for gases, we like to assume ideal behavior. Now, the ideal gas law only works when gases are behaving close to what we call ideal behavior. Now, what does that mean? Well, the ideal gas assumption is that we assume that gas particles do not experience any attraction or repulsion towards one another. In other words, if they pass by each other, there's no attraction, there's no repelling of each other. They just move on past. And that's a pretty good assumption under most conditions. We'll talk about conditions where gases do not behave ideally. Most of the time, gases that we work with in the lab under those conditions are very close to ideal gases, close enough to where we can just assume they're behaving ideally. The second assumption that we assume when we're talking about ideal gases is that we assume gas particles have no volume in comparison to the container that they're in. And this again is most of the time, well, it's not true, but it's most of the time close enough, right? Think about if you had $1 billion and you spent $1. Would you still think of yourself as having $1 billion? Probably, because you'd have $999,999,999. You're literally $1 away from $1 billion. So same scenario. Think about gas particles. They are so tiny. So when they're in a container, their size in comparison to the volume of the container is negligible. So these two assumptions are what we're assuming when we use the ideal gas law. We'll talk more about these later when we're talking about kinetic molecular theory in the chapter. So another thing we need to discuss is what's known as standard temperature and pressure, or STP. Now, you should know what it means when we're at standard temperature and pressure, i.e., you should know that standard temperature is 0 degrees Celsius or 273.15 Kelvin, and that standard pressure is 1 atmosphere of pressure or 760 torr. When I say a reaction is occurring at STP, you should know that that means these two conditions are 0 degrees Celsius for temperature, 1 atmosphere for pressure. Another aspect that I don't go as much into as some of my colleagues is molar volume. Molar volume can actually be used to calculate volume of a gas, but generally only when we're at STP. Now, if you think about when you're in a room, how often is the temperature 0 degrees Celsius? Not very often, because that's when water freezes. most of the time we're not under STP conditions, so molar volume doesn't really work all the time. Now, what is molar volume? It's the volume of 1 mole of gas, specifically at STP. And really, the volume of 1 mole of gas at STP is 22.41 liters per mole. Now, for every 1 mole, we have 22.41 liters of gas, and that's under STP conditions. You're not at STP, this number doesn't work. And so I don't spend a lot of time with this. Some instructors make you memorize that number. I'm not going to. I just reference it because you might see it in some of your Achieve homework. Okay, so let's do a problem. How many moles of gas, so this is what we're being asked to solve, are present in a 1.34 liter container at 3.65 atmospheres and 45.7 degrees Celsius? Now, this is a PV is equal to nRT problem, and I know that because I have temperature, I have volume, and I have pressure, and I was asked for moles, and we always have R is 0.08206 ATMs times liters over moles times Kelvin. Now, we have everything in the units we need it in too. Volume is in liters, pressure is in atmospheres, except for Celsius. We're in Celsius, we need to get that to Kelvin. So we know 45.7 plus 273.15 gives me my temperature in Celsius. This is 318.85 Kelvin, with actually the 8 being the last significant figure in the number. Okay, so now let's plug this in. We know 3.65 ATMs times 1.34 liters is going to be equal to N, what we're solving for, times 0.08206 ATMs times liters over moles times Kelvin. This is going to be times 318.85 Kelvin. And so now we can rearrange and solve for N, right? So if we do that, N is going to be equal to 3.65 atmospheres times 1.34 liters all over 0.08206 atmospheres times liters over moles times Kelvin times 318.85 Kelvin. And if we look at some units here, right, liters cancel, atmospheres cancel, Kelvin cancels, and we're left with 1 over moles, which is just the same thing as moles. So if we do this calculation out, we're going to get our answer in moles, which is what we were looking for. Our answer should be in 3 sig figs, and what we'll get is that we have 0.187 moles of gas in the container. All right, so if you have any questions, let me know. But let's move on to densities. So gas densities. Usually we list gas densities in grams per liter, and this is because their density is very small. Generally, gases have lower densities than solids or liquids, and we can actually derive the equation for density of a gas using the ideal gas law. We know that the ideal gas law is pressure times volume is equal to moles times R, our constant, times temperature. And we know that density is mass over volume. Well, if we want to derive density from the ideal gas law, we need to get mass somewhere in that equation. We already have volume, and we can do that using N. We know N is equal to mass divided by molar mass, right? Moles of anything is equal to the mass of that thing divided by its molar mass. So if we take this and we plug it into our equation here, we get that PV is equal to mass times R times T over molar mass. This gives me the variables of both mass and volume in my equation, which I can now rearrange and isolate mass over volume, right? So in other words, density of our gas is going to be equal to the pressure times the molar mass of the gas divided by RT, and that's what we have here. Now, this is pretty neat because density of gases is kind of a big deal. They're generally very low density, and it's why helium balloons actually float in air, because air has a higher density than helium does as a gas. It also is why hot air balloons work, right? If you think about what happens when we increase temperature, the density goes down. This decreases the density of the air inside the hot air balloon versus the density outside of it, causing the balloon to rise into the air due to the temperature difference. So let's do an example problem. A gas has a density of 2.60 grams per liter at 2 atmospheres and 300 Kelvin. What is the molecular weight or molar mass of the gas, right? So again, we have our density equation is pressure times molar mass over RT. We have T, we have pressure, we have R, we have density. So we can solve for molar mass, right? So I have 2.60 grams per liter is equal to 2.00 atmospheres times my molar mass of the gas all over 0.08206 ATMs times liters over moles times Kelvin times 300 Kelvin. And so if we look at some units here, we can rearrange and solve for molar mass, but we already have some units canceling, right? The kelvins, they're canceling, the atmospheres, they're canceling, and really we just need to get rid of liters so that we can get grams over moles. Now if we isolate this out, we get that the molar mass of our gas is equal to 2.60 grams per liter times 0.08206 atmospheres, liters over moles, Kelvin, times 300 Kelvin, all over 2.00 ATMs. And if we look at what's left unit-wise, right, again, liters, they're going to cancel here. Kelvin are canceling there. Atmospheres are canceling here, and what we're left with is grams over moles. This will get us a molar mass of pretty much 32.0 grams per mole. And there you have it. Okay, so if you have any questions, please let me know via Zoom or email.